All right, well, let's get started. Hi, welcome everyone. We're so excited to have you join us today. I'm Catherine from the MSU Science Festival. We're here to kick off our very first event of the year. We've gone digital, so thanks for joining us today. Today, during the Ask a Scientist, we're going live with 10 different scientists from a wide variety of different disciplines. This morning, I'm also joined by Roxanne Troon, who will also be joining us as a host. Hi, Roxanne.
Hello, everybody. Glad everyone could join us this Saturday morning.
All right, and today we're kicking it off first with astronomer Dr. Elias Aydi. Thank you so much for joining us this morning.
Thank you, Catherine. I'm really glad to join you today, and I would like to thank you for all the effort you have done to go live with the MSU SciFest during these difficult times.
Oh, absolutely. Just a reminder to everyone, Elias is here to answer all of your questions. So any curiosities that you have around astronomy, be sure to jump in the comments section and ask those questions there. So Elias, to start, do you want to just tell us a little bit more about yourself, what you study, the path you took to get here?
Sure. Well, I'm a postdoctoral research associate at the Physics and Astronomy department at MSU. I joined MSU around 2 years ago, and I do research on star explosion or stellar explosion, particularly a type of stellar explosions that we call novae. Novae comes from a Latin word, which is stella nova, or a new star, because these star explosions used to appear as a naked eye star in the night sky for the ancient astronomers. So they were thinking that there's a new star appearing. Actually, it's not a new star. It's a star that has been existing, but it had an explosion. And this explosion occurred particularly on the surface of a dead star in a binary star system. So we have two stars orbiting very close around each other. One of them is similar to our sun, and one of them is the core of a dead star, which we call a white dwarf. And I'm going to share my screen to show here what such systems look like. So we have the dead star here on the left-hand side, and then we have the sun-like star on the right-hand side. And usually the dead star is more heavy, and therefore it starts absorbing mass. It's like it's cannibalizing on the living star, on the sun-like star. And it absorbs this matter which accumulate on the surface of the white dwarf, on the dead star. And the density and pressure increase on the surface to a certain point where we have a thermonuclear runaway or thermonuclear explosion on the surface of the dead star, where the brightness of the systems goes up by 10,000 times or 100,000 times. And sometimes it appears as a new naked eye star. And then after the explosion is over, the system survives the explosion, and then the dead star goes back to its old bad habit of cannibalizing on its companion. And this is what we call novae. Now, why I study star explosions, I always say that I like to study star explosions because I think they are our ancestors. Because as you can see in the title of this slide, we are all made of stardust. Because when the universe started, when the universe started with a Big Bang, around 13 billion years ago, the universe was made from only helium and hydrogen. And when stars started to form, they started forging inside their cores the other elements that we see in our periodic tables. So the periodic table of elements that contains all these elements, all of these come from stars that forged them inside their cores or maybe during star explosions. So all the atoms that cause, or all the particles that are in our body, like oxygen, like carbon, nitrogen, and all the other elements like calcium that make our bones, all of them has been forged during star explosions. So always I say that star explosions are our real actual ancestors. Now, just to think about stars, stars like humans have a life cycle. They are born, they live, and then they die. And usually when we talk about stars, we divide them into two types. We have the sun-like stars, stars that are not very massive. And then we have massive stars, stars that are 8 up to 10 or even 100 times the mass of our sun. For sun-like stars, they all form from a giant cloud of gas and dust that collapse under its own gravity to form a star. But they don't die in a very, let me say, dramatic fashion. What happens is that the stars start to burn hydrogen into helium inside the core. So we have a core of a star, which is like a nuclear reactor, fusing hydrogen into helium. But at some point, this star will run out of its fuel, which is the hydrogen, and it will start to die. And our sun, which has been existing now for around 4 billion years or 4.5 billion years, after another 4.5 billion years or around 5 billion years, it will run out of its fuel and it will start to die. So this is what we think the life cycle of a star like our sun look like. So we have the star, which is born from a giant cloud of gas and dust, and then start fusing hydrogen in its core into helium and liberating a lot of energy that reaches us every day. And then the stars start to run out of fuel, it puff up in size. Our sun would become so big, it will turn into a red giant at some point where it runs out of fuel, and it will swallow all the inner planets like Mercury, Venus, and even our Earth. And then it will get rid of its outer layers of its mesosphere, and the remaining is the hot core of the sun. But during this process, the star will also burn helium into carbon and carbon into oxygen, and therefore it will start to create more heavy elements than hydrogen and helium. And therefore stars like our sun will contribute to the periodic table before they die and shed their outer layers into the universe or into the galaxy. So stars like our sun will contribute heavy elements as heavy as carbon and oxygen to the periodic table. But all the other elements are still missing. Where do they come from? Well, they come from the more massive stars. And these stars die in a more dramatic fashion. First of all, they don't live very long. Because they are massive, they consume their fuel even faster. So in a way, let's say live fast, die young. So stars like our sun will live for billions of years. However, more massive stars will live for millions or 100 millions of years. And therefore, they die much faster. And the way they die, it's much more dramatic. First of all, instead of turning into just a red giant, they will turn into what we call a supergiant. They are so big that here's a comparison between these stars, red supergiants like Betelgeuse and Antares, with our sun, which is this small dot over here. So Betelgeuse has been the focus of the news for now the past couple of months because it was showing some dimming and people expecting that, hey, the star might explode because it is now at the end of its lifetime and it turned into a supergiant. And at some point, this star will goes as a supernova. And while the star is going through this cycle, it will start producing more elements up to iron. So they will produce aluminium and cobalt and calcium and all the way to iron. But then these stars, while they're dying, they can't produce more iron. They need a really powerful explosion in order to turn into iron, and this explosion comes as a supernova. So during the supernova explosion, all the other elements heavier than iron, all the way to barium and plutonium and uranium, all of these are produced during supernova explosions. So if you want to make it as a summary, the universe started as during the Big Bang and produced helium and hydrogen. As I said, the stars started forging these heavier elements that we see in the periodic table. And when they died and when they exploded as supernovae, they enriched the universe with heavier element, which later formed new stars and new planets around them and new life. So when we say that we are all made of a stardust, it's not actually a cliche. We are indeed made of the dust of stars that died billions of years ago. Actually, every element, every atom in our body, as I said, comes from a star that died billions of years ago. And there's a very poetic thing that I always think about is that there's a high chance that the atoms that exist in our right hand probably came from a different star than the atoms in our left hand. And how poetic is that? For me, it's like the most poetic story in astronomy. I'm not sure if now there's people started posting different questions. Otherwise, I can keep going.
Yeah, we do have a
Catherine?
couple. We do have a couple questions.
Sure.
Let's see. Amanda wants to know, are there hypergiants from the biggest supernovae?
Are they hypergiants?
Are the hypergiants from the biggest supernovae?
So hypergiants or supergiants are the period or like the stage of the lifetime of a giant star before they turn into a supernova or before they collapse under their own gravity to make this giant explosion that we call a supernova. So supergiant or hypergiants are the stage of a life of a star that proceed a supernova.
Let's see. Other than the sun, what's the closest star to us?
Sure. So actually, I might have some. I'll share my screen soon. So of course, the nearest star to us is our favorite star, which is the sun. But when we talk about the next closest star to us, or the star that is closer to us outside of our solar system, it is actually a system of stars, of 3 stars. They are called Alpha Centauri. So most of the stars that we see in the night sky are not single stars like our sun. Most of them are either binary system, 2 stars orbiting their center of mass, or triple or quadruple systems, so 3 or 4 stars, all of them orbiting their center of masses. So the nearest star to us, which we cannot see from the northern hemisphere, and we can only see from the southern hemisphere, is called Alpha Centauri. It's made of 3 stars, Alpha Centauri A and B, orbiting closely to each other. And then there is a 3rd star, which is orbiting further away from them. And this star gets closer to us during its orbit, and we call it Proxima Centauri. Proxima because of its proximity to us. It's the nearest star to our solar system. And it is at 4.2 light years away from us. So a light year is a measure of distance. It's not a measure of time. It's the distance traveled by light during a year. So light, the fastest velocity or speed in the universe, 300,000 kilometers per second. So each second, light can cross 300,000 kilometers. It means it can rotate or orbit around Earth 8 times every second. It takes 4 years to get to us from Proxima Centauri. So just to try to understand these numbers, if we have a ship that can travel in the speed of light, we need 4 years to reach the nearest star to us, which is Proxima Centauri. And also, if you want to make a phone call with someone on one of the planets, that there are actually 6 planets around Proxima Centauri, there are 7 of them. And 2 of them, I guess, they are in the habitable zone, so they might host life. If you want to make a phone call, we will say hello. After 4 years, they will hear our hello, and they will reply. 8 years later, we will hear their reply. This is how long it takes us to communicate with someone on Proxima Centauri.
Great. Andrew is asking if you could discuss the labels planet and moon and Pluto. So why isn't Pluto considered a planet any longer?
So for so long, our solar system consisted of 9 planets, the 8 current planets, in addition to Pluto, the 9th planet back then. But in 2006, the International Astronomical Union decided to change the classification for what is a planet. And then for an object in our solar system to be classified of it needs to meet 3 criteria. These criteria are that this planet should have enough gravity that its shape should be rounded based on its gravity. And the second one is that this planet should be heavy enough that it cleaned its path around the sun. So while the planet is traveling around the sun, it should clean its path from all the debris and all the other objects that are in its orbit. And this is the criteria that Pluto actually couldn't meet, because Pluto is traveling in what we call near the Kuiper belt, where there's a lot of objects that are around it, and therefore it didn't clean its orbit around the sun, so it travels with a lot of other objects. And also the size of Pluto is not that big compared to the other planets. So planets like Earth, for example, which is a small planet, is still much more bigger than Pluto. And also there's one other thing, is that more recently we started discovering more objects like Pluto. And therefore Pluto and its new friends are now called the dwarf planets. We have now 5 dwarf planets in our solar system, but the expectation is that we will find hundreds maybe of these dwarf planets. And if we want to consider all of them as planets, it would be a big problem, especially for kids in school who would have to memorize 100 planets instead of just 8. So far, Pluto is a dwarf planet, and I guess it is good for everyone. There was some backlash because historically, well, all the other planets that are visible to the naked eye have been discovered since cavemen. We've all seen them with naked eye. But the other 2 planets, Uranus, Neptune, they have been discovered by European discoverers back in the 1700s, 1600s, etc. But Pluto was the only planet that has been discovered by an American discoverer. And therefore, there was a lot of backlash that, hey, we should keep the only planet that has been discovered by an American. But now the new criteria for that has been decided or adopted by the International Astronomy Union will put Pluto as a dwarf planet, which is I guess fine. Should not be sad about Pluto. He's happy with his other friends.
All right, Amanda wants to know, if you were a photon traveling across the universe at the speed of light, in your perspective, would time be stopped and also infinitely fast at the same time?
Can you please repeat that?
Yes. If you were a photon traveling across the universe at the speed of light, in your perspective, oh, I lost the comment.
In your perspective, with time freezes, I guess maybe that was it. Well, we know that, well, based on the theory of general relativity of Einstein, we only massless objects can travel in the speed of light, and a photon is a massless object. Based on the theory, if we manage to reach the speed of light, time freezes. So yes, in the perspective of photon, the time might freezes. Would we be able to travel in the speed of light at some point? Well, so far we say it's impossible. But personally, I would never like to say that something is impossible. Because if you want to just take an example, and say you go back just 100 years ago in time and say to someone that, hey, I can pick up something from my pocket, a very small object, and you can use the object to see and talk to someone on a different continent. They would say, this is impossible, you're mad, you're crazy, this is not possible. And now we live as it is normal in our life. We pick up this device from our pocket and we talk with people in different continents. We can see them. So in 100 years from now, we might be laughing ourselves to say that traveling the speed of light is impossible. So I always like to say that everything is possible. We just have to give it time. Actually, I have a tattoo on my hand that says, believe the impossible.
All right, another question from Stella. Stella would like to know why you decided to become an astronomer and what are some of your favorite parts about being a scientist? So what inspired you?
Well, I always loved physics and I always wanted to be a physicist for some reason. I loved physics since I was in school. And I guess astronomy was the subject that captured my attention the most. I always wanted to know what's happening up there. I wanted to understand the stars. I always was fascinated by stars and black holes and neutron stars, and I wanted to learn more about them. And for me, astronomy is not a job. It's more of a hobby. It's like a passion. And this is I guess, the best part of being a scientist. I never feel like I'm going to work. Actually, I'm always excited when I'm going to work because I want to study new data, which I'm looking forward to see what's in this data, what I'm going to discover today, if there's something interesting that I'm going to discover. So of course we have our days where we're like, I'm tired and maybe today I don't feel like going to work, but in general, I really don't feel like I'm working. And this is, I guess, one of the best feelings for a researcher. We are privileged, like we're maybe one of the few people that can say, I'm like to go to work, because we really do. We really enjoy going to work and discover new things. So I guess it's a passion more than a work.
That's great. All right, so it's 10:22. We have a couple minutes left. If you have any questions, be sure to type them into the comments section there. So Elias, you have another talk next week.
Yes, so that's actually good time to promote for another event coming next week. On Monday the 13th, I will be talking more about stars and star explosions. I will be giving a talk also online, which is entitled Stellar Evolution and Our Ancestors. So I'm going to talk about the evolution of stars and how these stars are actually our true ancestors. And this would be on April 13th at 7 in the evening Eastern Time.
And you can find all that information on our Facebook page and on our website at sciencefestival.msu.edu. All right, so we can take one more question here. Grace would like to know, what is the largest star?
Oh, so the largest star, so of course there's always uncertainty when you talk about the largest and biggest, and because there's always uncertainty on the measurements in astronomy, so we can't always give an absolute value. But one of the largest stars known is VY Canis Majoris. It is a star that could be seen from the northern hemisphere. You can Google it. I guess it is, I can't remember the exact number, maybe a bit less than 2,000 times the sun, the mass sun, but VY Canis Majoris is so far one of the largest stars known.
All right, let's see. It looks like we have a couple more minutes. Let's see. When the Andromeda galaxy collides with the Milky Way, what does that look like?
Okay, so the collision is going to be very smooth because the distance between the stars and the galaxy and the Andromeda galaxy are so vast. As I said, the nearest star to us is 4 light years away from us. So it's not going to be like a really explosive merging between the two galaxies. It's going to be a smooth merge between the two galaxies. Stars will pass really far from each other. What could get a little bit chaotic is the centers of these two galaxies, where we have supermassive black holes. Not sure if like the two black holes will join and form an even bigger black hole, but for the other stars, going to be something relatively smooth.
Great.
Yeah, and I want to correct one thing about the size of VR Canis Majoris is the biggest, but not the mass. The mass is like 20 times maybe the sorry, I said mass, it should be the size. Mass is around 20 times or 18 times the mass of the sun, but the size is one of the biggest.
Great, awesome. Well, thanks so much, Elias, and thank you everybody for tuning in. Elias is going to be hanging out for a little bit in the comment section, answering some of your questions. I know there are a few that I missed. And stay tuned. We're going to be live throughout the day with different scientists until about 4:30. So stay tuned for more. Thanks so much.